Welcome back to Nick's Algebraics. Today I'm going to introduce some basic concepts in trigonometry. And with me today I have a random guy and the former math club secretary.
Hello! That was in the last three videos.
And as usual, I'm going to put the blank and filled out notes in the description so you guys can all follow along at home. Let's start off by defining what trigonometry is. Trigonometry literally means measurement of triangles. So it comes from the Greek words trigon, meaning triangle, and metron, meaning measure. So let me highlight that because that's important. So basically, trigonometry is a branch of mathematics that studies the relationship between angles and side lengths of triangles. So using the side measures of a right triangle and some angle theta, we can form six trigonometric ratios. So basically, a trigonometric ratio is a ratio of the lengths of two sides in a right triangle. So it can be maybe,
Ratio of trigonometry, you could say.
what do you mean by that?
Well, you could say it's a ratio trigonomically, correct?
Oh, because it's a trigonometric ratio?
You could say.
It's a ratio that's trigonometric?
Yeah, you could say that. I would say that,
I,
probably.
I guess you can say that, yeah.
Thanks for that. Thanks for the validation.
Of course, of course. When you hear the word ratio, think like division. So we're getting one side length divided by another side length in some right triangle. And these six trigonometric ratios are functions. They're functions of some angle theta. That's what we use for angles. We use theta. That's the most popular, Greek letter for that. Let's talk about just the different kinds of side lengths, the different kind of sides in a right triangle. So, does anyone know what the longest side in the right triangle is called?
That's going to have to be the hypotenuse.
Absolutely. It's the hypotenuse. The hypotenuse is the longest side in a right triangle, and it's opposite the right angle. It's like across the right angle. And
Everything we've used so far is Greek.
exactly. Do you know what the other two sides are? The two like shorter sides. What are those called?
I do not. Those are called the two shorter sides, but more specifically, the one that is across from theta is going to be the opposite, and the one that kind of touches it is the adjacent.
Okay, that's correct. This is the side opposite theta, and this is the side that's adjacent to theta. It's like right next to it. But the word I was looking for is legs. These are the legs of the right triangle. Those are the two.
That's lame. That's stupid. You said that's correct in a way that implied it was not correct, and you gave me a less specific replacement for what I said. What the heck?
Yeah, it be like that. But yeah, the hypotenuse is the longest side, and the two shorter sides, those are the legs of the right triangle. And like I said, this is the opposite leg. It's opposite the angle, and this is the adjacent leg. It's right next to the angle. Let's talk about these six trigonometric ratios. So the first one we're going to talk about is sine. So sine, it's abbreviated sin. We just dropped the E because we're lazy like that. So sine of some angle theta, that's defined as the length of the leg opposite angle theta. So it's the length of the opposite leg over the length of the hypotenuse.
And I sign off on that.
Yeah, yes. So that's what sine of theta is. So let's just do a little bit of example one. So for example one, we're trying to find the values of all six trigonometric ratios. So for this triangle, let's start by finding the value of sine of theta. Sine, like I said, it's the length of the leg opposite angle theta. So that's this leg right here. It's 3 over the length of the hypotenuse right here. But we don't know the length of the hypotenuse right now. All we know are the lengths of the legs. So how are we going to find the length of the hypotenuse?
Perhaps there's a certain theorem that relates side lengths in a right triangle we could use. Maybe the theorem that begins with P and ends in agoras.
Never heard of it.
Pythagoras.
We're gonna use the Pythagorean theorem.
Just realized it said Pythagoras theorem instead of Pythagorean theorem. So we're gonna change it to Pythagoras theorem now.
Why not? Yeah. So the Pythagorean the Pythagoras theorem and the Pythagorean theorem says that a squared plus b squared equals c squared. So a and b are the lengths of the legs, and c is the length of the hypotenuse. So I'm going to call this side c. So a squared plus b squared, that's 3 squared plus 4 squared, equals c squared. So 3 squared is 3 times 3, which is 9. 4 squared is 4 times 4, which is 16. And 9 plus 16 is 25. So if c squared is 25, what does that make c?
It would make it plus or minus 5, except, negative side lengths. It's a little bit wonky, so we can just pretend it doesn't exist.
Exactly. So it's just 5. So that's the length of the hypotenuse using the Pythagorean theorem. You get 5. So this is a classic 3, 4, 5 right triangle.
Classic.
Yeah, very classic.
And any good trig student would have that Pythagorean triple memorized, but I'm just going to point out that on your tests, they're always going to use a few of the same triangles that have this nice property of perfect squares. So if you just memorize some triangles, you can just bypass a lot of the work. You should still show it though.
Yeah. So back to sine of theta. So sine, it's the length of the opposite leg, which is 3, over the length of the hypotenuse, which we just figured out is 5. So sine of theta for this triangle is 3 over 5. All right. Now let's talk about cosecant. So cosecant is the reciprocal of sine of theta. So
We're doing cosecant before cosine.
that's right.
This is uncharted territory. No one's ever done it like that before.
I'm built different.
Wow. A little travesty, honestly, but
This is controversial.
I like it controversial. So cosecant, it's abbreviated CSC. So cosecant of theta, like I said, it's the reciprocal of sine. So instead of the length of the opposite leg over the length of the hypotenuse, now it's the length of the hypotenuse over the length of the opposite leg. So it's hypotenuse over opposite. So if sine of theta is 3 over 5, what does that make cosecant of theta?
The reciprocal of that.
Which
you
is
make it 3 over 5 flipped.
exactly, it would be 5 over 3. So, and you can literally check that. You can see like hypotenuse over the opposite leg, the length of the opposite leg. All right, now let's do cosine. So cosine is abbreviated cos, C-O-S. So cosine of theta is defined as the length of the leg adjacent to theta. Adjacent basically means like right next to, over the length of the hypotenuse.
And I'm co-signing on that.
No, you have to sign it and then I co-sign it.
You got it.
And
I'm signing on that. Random guy, can you co-sign on that?
yeah. I can co-sign on it if you give me a red pen, but another color would be better.
I'll cosecant on that. Okay, I'm not a comedian.
No, we make the jokes. You just do the math and we make fun of you.
Okay, silly me. So cosine of theta, the length of the leg adjacent to theta is 4. So, and the length of the hypotenuse is 5. So cosine of theta for this triangle is 4 over 5. And then for secant, that's the reciprocal of cosine. So secant, it's just abbreviated SEC. And instead of adjacent over hypotenuse, it's hypotenuse over adjacent. So if cosine of theta is 4 over 5, what's secant of theta?
Well, my first thought was wrong, but my secant thought is that it's 5 over 4.
Wow, that's right. Okay. And then we have tangent, which is abbreviated tan. So tangent of theta, that's the length of the leg opposite theta over the length of the leg adjacent to theta. So it's opposite over adjacent.
Honestly, I could do without this one. It's only like tangentially related to the topic.
All right, so tangent theta. So like we said earlier, the length of the opposite leg is 3, and the length of the leg adjacent to theta is 4. So it's 3 over 4. And the last trig ratio is cotangent, which is the reciprocal of tangent, abbreviated cot. And instead of opposite over adjacent, it's adjacent over opposite.
Hot, that one doesn't make a whole lot of sense to me. I think I'm gonna have to sleep on it. Not my best work, but we'll take it.
So if tangent of theta is 3 over 4, what's cotangent of theta?
You've got to be kidding. It's 4/3.
That's right. Yes. And you can double check. You can see like adjacent is 4 over opposite, which is 3.
An interesting point here is that sine, cosine, and tangent never seem to exceed 1, and the reciprocals are always exceeding 1 or like equal to or exceeding. If you graph these functions, that'll become more apparent. I don't think we're doing that in this video.
Yeah, definitely beyond the scope of today's video. But you might have noticed there's a little bit of a mnemonic device for learning the ratios of sine, cosine, and tangent. It's called SOHCAHTOA. So we're using the first letter of each word in the ratios. So the S is for sine, O is for opposite, H is for hypotenuse. So that's so. And then ka is cosine adjacent hypotenuse. And then toa is tangent, opposite, adjacent. So SOHCAHTOA, that's how you can remember the ratios for sine, cosine, and tangents.
I would just remember it, but that's helpful.
Absolutely. And there's just two important things to recognize. Theta has to be an acute angle in a right triangle, which is what's happening in this figure right here. And the second note is sine of theta, it's not sine times theta. It's not a product. It's sine of theta. Sine is a function of theta. It's kind of like square root of x. It's not square root times x. So it's a function. And the sine function, what it does is it takes an angle as its input and it outputs the ratio of the length of the opposite side to the length of the hypotenuse in a right triangle. All right, so let's do example 2. So find the value of x, round to the nearest tenth. So we got this triangle, we have some angle, we have the length of the hypotenuse, and we need to find the length of this leg right here. And what leg is this? Is it opposite the angle 41 degrees or is it adjacent?
Was the failed math club secretary gonna say?
I was going to say I wasn't listening, so you're going to have to repeat yourself. But off a pure guess, it'll be the adjacent.
Absolutely. That was a very great guess. So this side is adjacent to this angle right here, 41 degrees, because it's right next to it. So we want to find the length of the adjacent side, and we have the length of the hypotenuse. So what trig ratio has adjacent and hypotenuse in it?
A over H, cosine.
Exactly. So we're going to use cosine. So cosine of this angle, cosine of 41 degrees, it's the length of the side adjacent to that angle, so x, over the length of the hypotenuse, which is 11. So how are we going to solve for x? What do I have to do to get rid of that 11? We need to...
I guess we'll multiply by 11 to both sides.
Exactly, multiply both sides of the equation by 11. So on the right side, the 11 will cancel. And you'll get x equals 11 times cosine of 41 degrees. And if you put this in your calculator, you'll get that x is approximately equal to 8.3.
Alternatively, you could not use a calculator and figure this out using a Taylor series approximation.
Of course, yeah. That's also very valid. But yeah, I purposely put 8.3 because it says round to the nearest tenth. That's why I'm cutting it off at the first decimal place.
How would you be watching a trick video if you knew Taylor series already?
That's a very great question.
I'm in the video and I don't know Taylor series.
Yeah. So you're in the right place. So
Watch that video next.
yeah. But At the end of every problem, it's a good idea to check if your answer is reasonable. The length of the hypotenuse is 11. That's the longest side. So we expect that our answer has to be less than 11, which it is. It's 8.3. So that makes sense. If you got like 13.4, then you know that you messed up because your answer should not exceed 11. Because, like I said, the longest side has a length of 11. All right, let's do part B. So now we need to find the length of the hypotenuse. And we have two angles now. So which angle should we use? Does it make a difference?
I think it depends on like the angle with which you approach the problem. So maybe I think we should do it both ways. So the first way, look at the 62-degree angle and be like, oh, hey, that we know the side adjacent to that, and we're looking for that x hypotenuse. So maybe that cosine of 62 degrees is equal to 50 divided by x, and then you solve for x. That's one way you could do it.
Mm-hmm. The other way is you can use the 28-degree angle and use sine because we have the length of the opposite leg and we're trying to find the length of the hypotenuse. So it doesn't matter which angle you use. I'm just going to stick with the 28-degree one.
Reasonable.
So we have to use sine if we're going to use that angle. So sine of 28 degrees, it's the length of the opposite leg, which is 50, over the length of the hypotenuse, which is x. So how are we going to solve for x? This one's slightly different than the last one. We can't just like multiply by a number now and like just have it by itself that quickly.
I suppose we multiply x to both sides and divide by sine of 28, which is the same as multiplying by cosecant of 28.
Absolutely. So multiply both sides by x. So you get x sine of 28 degrees equals 50. And then divide by sine of 28 degrees. So x equals 50 over sine of 28 degrees. The shortcut is that you can just switch these two pretty much if you don't want to multiply by x and divide like every single time, because this kind of situation happens a lot. So using your calculator, if you punch in 50 over sine of 28 degrees, you're going to get, if you round to the nearest tenth, you're going to get 106.5.
I would just like to point out that if we had used the other angle and instead used cosine of 62 to work this out, we would have gotten 50 over cosine of 62. And that would seem to imply that sine of 28 is the same as cosine of 62. So the sine is equal to the cosine of the complementary angle. Very, very interesting.
Very, very interesting. So let's just check that our answer is reasonable again, because remember the hypotenuse is the longest side. So it should be longer than 50, which it is. We got 106.5, so that makes sense. If we got 30, then you know you messed up because that would make one of the legs longer than the hypotenuse. All right, let's do a slightly more complicated problem. Let's find the values of x and y now. So to find x, all we need to do is look at this triangle right here. If we're using this angle, the 56-degree angle, x is the side adjacent to that angle, and 10 is the side opposite that angle. So which trig ratio should we use to find x?
Well, going by SOHCAHTOA, we should go with tangent. Yeah, tangent's the only one, also cotangent, I guess, that doesn't have the hypotenuse in it. And since we don't know the hypotenuse of the triangle, we're given that be the easiest to use.
Absolutely, yeah. So we're going to use tangent. So tangent of 56 degrees, it's the length of the opposite side. So 10 over the length of the adjacent side, which is x. So this is similar to last time. How are we going to find x?
Oh, you're switching those bad boys around.
Absolutely. We
X
can
and tangent of 56.
exactly. We can just use our little shortcut and switch the two. If you want to do it the long way, you can multiply by x and divide by a tangent of 56 degrees, but just switch them. It's the same result.
Would I get points docked for not showing my work?
Ooh, that's a very great question. At Nick's Algebraics, you will get full credit for using the shortcut. So you're good.
Not rigorous. I would have gotten points taken off if I did that.
Yeah, it's traumatizing. So if you punch in 10 over tangent of 56 degrees in your calculator, you're going to get, of course, rounded to the nearest tenth, you're going to get about 6.7. All right. Now we need to find y. Any ideas on how we're going to do that?
I have an idea.
What do you think?
Well, one thing we could do is kind of look at this as one giant triangle. We see that the opposite of the 34-degree angle is 10, and then the adjacent is just x plus y together.
Exactly.
And we already know x.
That's right. So from there, we can find y. Is that what you were going to say, Secretary?
Oh, that was precisely what I was going to say.
Excellent.
That's just one big old triangle.
That's right. That little thing right there, it's just there to confuse you into thinking that this triangle really is important. But we found this side right here. So that side is 6.7. We can find the length of the hypotenuse here. And what would be the problem if someone said, oh, let's do tangents, because we have this side now and I want to find the adjacent side of y. Is that also valid?
No,
Absolutely not.
And what's wrong with that?
Completely invalid. Looks to me like there's no right angle in this triangle.
There we go. That's exactly what I'm talking about. So that's what I said right here.
Yeah, that ain't right.
It has to be in a right triangle. So we cannot do that. So we have to use this big triangle right here because that's a right triangle. And we need to find a piece of the side adjacent to this angle. And we have the opposite side. So we're going to have to use tangent again. So tangent of 34 degrees is the length of the opposite side. Because again, we're looking at this entire triangle here. The length of the opposite side is 10. And the length of the adjacent side, which is this entire side right here, is x plus y.
But we know x, don't we?
Exactly. So we know x is 6.7. So I'm going to replace x with 6.7 here.
Whoa, you're directly plugging in the approximate answer?
That's right. You should keep a couple more digits, but for this problem, you'll see that it won't really matter.
This is unacceptable.
Just a little bit. Just trying to keep people on edge.
No, you should have done 10 over tangent of 56.
You could, if you want to be super precise, you can definitely plug in 10 over tangent of 56 degrees for x.
I'll be the first to say I'm not that guy.
There we go. Yeah. I'm going to use my little shortcut. So I'm going to just switch the denominator and the quotient here. So I can say 6.7 plus y equals 10 over tangent of 34 degrees. And to get y totally by itself, I need to subtract 6.7 from both sides. So y equals 10 over tangent of 34 degrees minus 6.7. And if you put this all in your calculator, you're going to get about 8.1. Okay.
Could have been better, but
So there's a relationship between sine and cosine that's very interesting that I wanted to talk about. We got this triangle here, this right triangle. And how would I find this missing angle right here?
could you start by giving it a variable name?
Sure, let's call it
I like to use
alpha. Okay.
what were you going to use?
I was just going to say x, but we should probably stick with the.
That's for side lengths more commonly. I used alpha when I was in pre-calc, and everybody started using it. I started that trend.
So would you say you're an alpha?
Yes, I am an alpha trigonometer.
Wonderful.
So you were asking how do we find alpha?
Mm-hmm.
Well, we know that we're doing degrees, not radians, right?
Yeah.
All right, cringe, but whatever. So we know that there are 180 degrees in a triangle. So therefore, 180 degrees must be equal to theta plus alpha plus 90 degrees, which is that right angle.
That's
Then
right.
we can just solve for alpha.
Exactly. Those three interior angles add up to 180 degrees. So to solve for alpha, I'm going to subtract 90 and subtract theta. So if you subtract 90 the right side becomes 90 degrees. And if you subtract theta, you just get 90 degrees minus theta. So that's this angle right here. So alpha, which is 90 degrees minus theta right there.
In other words, these are complementary angles.
Exactly. These two angles right here, they're going to add up to 90 degrees. You can see like theta plus 90 minus theta, like the thetas will cancel and just get 90 degrees. So let's find sine of this angle theta here. Remember, sine is the length of the opposite leg over the length of the hypotenuse. So what would that be?
Oh, that's B over C.
It would exactly, it would be B over C. And notice how that's the exact same thing as cosine of the other angle, cosine of alpha, which is cosine of 90 degrees minus theta. If you do cosine of this angle right here, that's the length of the adjacent leg, which is B, over the length of the hypotenuse, which is C. And you can do this the other way around. You can say cosine of theta. Cosine of theta is the length of the adjacent leg, which is A, over the length of the hypotenuse, which is C. So cosine of theta is A over C. And this is the same thing as sine of the complement of theta, which is alpha, which is 90 degrees minus theta. You can see sine of this angle right here. Opposite leg is A, hypotenuse is C. So if two angles are complements, remember, two angles are complements if their sum is 90 degrees. So for example, angles of 70 degrees and 20 degrees, those are complements because 70 degrees plus 20 degrees is 90 degrees. So if two angles are complements, then the sine of one equals the cosine of the other. So because of this relationship, we say that sine and cosine are cofunctions of each other. So that's our vocab word, cofunctions. They're any pair of trigonometric functions, f and g, for which f of theta equals g of 90 degrees minus theta, and g of theta equals f of 90 degrees minus theta. So that's where the names of these trig functions, these trig ratios come from. Like the co in cosine stands for complement because cosine is the complement of sine. So the cosine of an angle is the sine of its complement right here, as you can see. So the relationship is what the name reflects.
There's a lot of etymology in this video. Way too much for math. There's too much language.
Yeah, Secretary?
That's what happens when you mess with the Greeks. Let's put it that way.
That's right. That is absolutely right.
Also my fault, suggesting alpha. Too many Greek letters. I have contributed to the problem.
Yeah, it got very Greek very fast in here. But yeah, it's the same idea with cosecant and secant and cotangent and tangent. The co just means complement. So for example, sine of 30 degrees, that's going to equal cosine of the complement, which is 60 degrees. Those two angles add up to 90 degrees. So let's do an example. So find a cofunction with the same value as the given expression. So we have sine of 72 degrees. So we know this is one of our cofunction identities. We know that sine of theta equals cosine of 90 degrees minus theta. Let me write that out. So sine of some angle theta equals cosine of 90 degrees minus theta. So in this case, theta is 72 degrees. So sine of 72 degrees equals cosine of 90 degrees minus 72 degrees. And 90 minus 72 is just 18. So sine of 72 degrees equals cosine of 18 degrees. So you can see that the value of a trigonometric function of theta is equal to the cofunction of the complement of theta. You can see that 72 degrees and 18 degrees, they're complementary angles. So cofunctions of complementary angles are equal.
Wow. Stunning.
Absolutely. And let's just do one last example with cotangent. It's the same idea. Cotangent and tangent are cofunctions of each other. So we know, I wrote it right here, cotangent of theta equals tangent of 90 degrees minus theta. So in this case, theta is 8.1 degrees. So cotangent of 8.1 degrees equals tangent of 90 degrees minus 8.1 degrees. And 90 minus 8.1 is 81.9 degrees. All right, and again, you can see 8.1 degrees and 81.9 degrees. Those are complementary angles. They add up to 90 degrees. All right, that's all I got for today. So make sure to like, subscribe, and comment down below what's your favorite trig function? What's your favorite trig ratio? And you can also comment what you want me to make a video on next. I'll see you guys in the next video.
Bye.
Bye.